One of the most popular converters at high powers is the full bridge converter. The topology is like this. You have 4 switches. In fact, it is comprised of 2 half bridges. See, you have one arm, switch 1, switch top. You have one top switch and bottom switch. You have another arm, one top switch, another bottom switch connected like this, and both arms are connected to VDC in this fashion. Now, if you take the center points of these 2 bridge arms, we connect the transformer across them. So I am completing the circuit with body diodes for the sake of completeness. They help in during freewheeling operations. So you have Q1, Q2, Q3 and Q4. So across the center points, we will connect the primary of the transformer, the secondary of the transformer. Like in the case of the half bridge, you have the 2 diodes, and with respect to the center tap, we have the inductor, capacitor and the load, which is operating as a buck derived converter. It's a buck operating in the buck mode, but with ORing effect, as in the case of push-pull and also as in the case of the half bridge converter. Operation is exactly similar. Now this V0, so C, L, I will put the dot polarities like this. Now let us, this VDC, let us consider the case you are now operating the switches in pairs. Q1 and Q4 will be turned on simultaneously. Q2 and Q3 will be turned on simultaneously. However, when Q1 is on, Q2, Q3 will be off. When Q2, Q3 are on, Q1, Q4 are off. So Q1, Q4, when they are on, Q1 is on means that the non-dot end is connected to VDC. The dot end is connected to ground through Q4. So what appears across the primary plus minus is in this fashion. So the non-dot end is minus, dot end is plus. This is the pole voltage Vp. So let us look at that. So when you measure across the primary, you get VDC measured in this fashion, and the non-dot end being positive, the bottom diode here is active, and then it will supply power to the inductance. Vp will be N times VDC. If you take a turns ratio 1:n, so Vp will be N times VDC. We'll write it down. And during the time when Q2 and Q3 are on, these two are on simultaneously, you will see that Q3 is on means dot end is positive and non-dot end is negative. Q2 connects it to ground. So secondary side also you will see the dot end positive, non-dot end as negative. So the primary voltage is VDC. It will translate into N times VDC, and Vp will be N times VDC during that time. And during the time when Vp is 0, when is it? When all the 4 switches Q1, Q2, Q3, Q4 are off. So when all these 4 switches are off, the inductor current is freewheeling, and like as before in the case of the push-pull converter and in the case of the half bridge converter, the secondary side is center tap. The inductor current splits here exactly by half into the top winding and into the bottom winding. It goes into the dot end in the bottom winding. It goes into the non-dot end in the top winding. The MMFs so generated are opposing and cancel each other in the core, and the flux does not change. So d phi by dt is 0, and therefore the induced voltage across all the windings are 0, and Vp will be 0, and so also the voltage across the primary. So therefore, when you take V0 is with respect to Vp. This is N times VDC. Vp is having double the duty cycle as that of the switches. So N times VDC into 2D. And rewriting 2 into N into VDC into D. Now this is the input-output relationship for the full bridge converter. Now let us say VCO rating for the switch, like in the half bridge, is maximum VDC. So when Q1 and Q2 are on, Q2, Q3 are off, and you will see that Q2 is connected to VDC, Q3 is connected to ground through Q4, and therefore Q3 has to withstand VDC, Q2 has to withstand VDC. Now when Q2 and Q3 are on, Q1 is connected to ground, Q1 has to withstand VDC, Q4 is connected, collector is connected to VDC, and Q4 has to withstand VDC. Therefore, all 4 switches need to withstand VDC and they have to be rated for greater than VDC. In the half bridge converter also, each of the switches were supposed to be rated for VDC. Only in the push-pull converter, the switches need to be rated for 2 times VDC. Now, in the case of the full bridge converter also, we see that there is a requirement for solving the flux walking problem. Wherever this kind of a situation occurs where you are having switches and practical or non-ideal switches, and you are having a winding connected in this fashion, there is a chance of an average voltage occurring across the V primary. Because when Q1 and Q4 are on, the voltage across the primary will be VDC minus VC sat of Q1, VC sat of Q4. And when Q2 and Q3 are on, it is VDC minus VC sat of Q2, VC sat of Q3. All the VC sats Q1, Q2, Q3, Q4 will not match, and therefore there can be a primary average voltage, and this will get integrated, and there will be a flux which will have a proportionality with respect to time, and the flux will be increasing with time and ultimately saturate this core. Therefore, you need to provide flux walking, and just like in the case of the half bridge and push-pull case, you can provide flux walking by adjusting the duty ratios of Q1, Q4 and Q2, Q3 set. Alternately, like in the case of the half bridge, you have the primary winding which is a single winding, not center tapped. Therefore, you can place a capacitance, a flux walking capacitance, which will prevent an average flux occurring in the winding, and the CFW or the flux walking capacitor will absorb the average voltages. So in this way, flux walking can be avoided in the full bridge also, but note that full rated current has to flow through the capacitance here. Now let me mark I primary and V primary here, and what is the difference between half bridge and full bridge. For a given power, given output power, let us say in the case of the half bridge, the primary voltage is VDC by 2, recall, and let us say the primary current is some value IP. For the full bridge case, for the same power, if you take V primary voltage is VDC, that is fixed by the topology, and the primary current for the same power has to be half as that of the half bridge, should be IP by 2, so that the product VDC by 2 into IP and VDC into IP by 2 are the same to realize the same power. Therefore, in the case of the full bridge converter, to realize the same output power, you need to rate the switches half of that of the comparable half bridge converter, and this is the advantage of the full bridge converter. However, you need 4 switches and 4 gate drives for the full bridge converter, as against 2 switches and 2 gate drives for the half bridge converter.